All right, so welcome to Wake Tech's chemistry class. So this is some stuff we will go over on the first day, and hopefully you realize scientific notation. It's part of the math background you're really going to need to understand this year. And I bring this up at the beginning because I think the fact that chemistry is a math class takes some people by surprise. So what we have here is powers of 10. So scientific notation is always in the style of 1 to 9.99, whatever, 2 times 10 to some power. So we will have numbers like 6.02 times 10 to the 23rd. And we'll discuss that more, but basically we have a positive power of 10 here. So that means it's a huge number. Okay, that means that there's basically 6 with 0, 2, and then 21 zeros after that. So we're talking about a huge number. And you should know that when that's positive, you have a huge number. When it's negative, and I'm trying to think of a thing we'll use where it's negative. So off the top of my head, something like 6.38 times 10 to the minus 7 meters, which is the wavelength of visible light. Some visible light. Off the top of my head, I can't think of it, but it's something. It's like blue. Now that has a negative exponent. So what that is it's a very small fractional number. It's 6 zeros and then a 638. So this number translates to a very small number. This number translates to a very large number. And that's because the power of 10 is telling you which way to move the decimal point. Scientific notation is always going to be between 1 and 9.9999. So notice this number here, this number here. I put them both at 6. They are always going to be between 1 and 9.999. And that the exponent is telling you how many places to move the decimal. So if we were going to practice some more of this, if I ask you to put this into decimal notation, and this time I won't use a 6. Okay. First of all, is that going to be a negative exponent or a positive exponent? Since that's a fractional number, hopefully you're thinking that should be a negative exponent. So we're going to have it to the negative power, and we're going to move that decimal 1, 2, 3, 4, 5, 6, 7 times. So that's 10 to the minus 7. Nothing if not consistent, kids. And that's 8.36, even though I told you I wouldn't use a 6, times 10 to the minus 7. So likewise, if I had a number like 1800, all right? So a huge number, so we're going to need a positive power 10. You're going to need to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So you're going to need to move that 10 places so that you get a number between 1 and 10. And that number between 1 and 10 is 2.18. And then that's going to be times 10. We moved it 10 spaces. So times 10 to the 10th. All right. That is section. All right, so here is matter. So matter is anything that has mass and takes up space. Mass is a measure of the amount of stuff. It's not the weight of something, even though we always use a balance or scale to figure out what the mass is. It's supposed to represent how much stuff there is in something. So if you think about it, here's a person on Earth and he weighs 100, let's say 100 pounds. If that same person were on the moon, we know hopefully from watching things on television and whatnot, that he would weigh significantly less, and would weigh 16.6 pounds. So doesn't it make sense that what's in this person didn't change from the Earth to the moon, and that there should be some representation of the stuff that's inside of him? So we call that stuff inside of him the mass. So mass is unaffected by gravitational pull. So even though the Earth has more gravity pulling down on him, and that's why he weighs more on Earth than the moon, which has very little gravity, there should be some measurement of the amount of stuff inside of him, the little particles and whatnot, material that makes up the sky. And that should be true of anything. So we call that the mass. So mass is not weight. It's, unfortunately, to confuse you, used measured on a scale and whatnot. But mass has the units of grams. So this will be grams, and that's important. So the other thing we're going to talk about is how matter is broken down. Now, maybe you're familiar with how animals can be broken down into those with backbones called vertebrates and those without backbones called invertebrates, and that vertebrates can be broken down further into mammals and reptiles and fish and amphibians and birds, whereas invertebrates can be mollusks or arthropods and then whatnot. So that kind of a breakdown is what I'm looking to accomplish here. The entire universe can be broken down into either matter or energy. So everything can be either in the universe can be classified as either matter, having mass, right? So mass in grams, or energy. So not having something you can not physically stuff there, but has more to do with motion or heat or that kind of thing. So matter, that's not pretty grams, can be either defined as a pure substance or a mixture. So getting into that, matter being a pure substance or a mixture, what are the differences? Well, pure substances can be one of two things, either elements on the periodic table, okay, or compounds, which are groups of elements from the periodic table. So those are the only two ways of a pure substance. Examples of elements would be just like gold is Au, carbon is just C, neon is Ne. Those are just elements. Compounds would be something like methane gas is CH4, so it has carbon and hydrogen, water, H2O, okay? Hydrogen and oxygen together, always in the same ratio. So compounds will always have elements in the same ratio, whereas elements are just elements right off the periodic table. Now you can break compounds down further into ionic and covalent. Ionic being a metal plus a non-metal. That's ionic. And covalent is only non-metals. Now what do you mean, Mr. Roach? Well, elements can be either metals, metalloids, or non-metals. So do I get into it here? I don't get into it here, but I'll show you in a minute what all that means. Well, basically where they are on the periodic table. I can bring it up now. So here's a quick and dirty periodic table. There's this staircase that goes sort of this way, and everything on this side is a metal, and everything on this side is a non-metal. So if in any time of your life you're like, oh, I forget which side are metals and which side are non-metals, just start looking around at some of the elements and you'll recognize some names as metals or some names as non-metals. Oxygen is up here, and hopefully you realize oxygen is not a metal, it's a gas. Whereas iron and gold and silver and those type of things, copper, are metals, and they're going to be on this side of things. All right. Mixtures can be either homogeneous, which means you can't see where one thing begins and another ends. So sort of clear juices is an example of that. Mixtures of metals, like if you think about brass instruments, how you can't see where the copper atoms begin and the zinc or iron atoms end. Heterogeneous would be a mixture where you do see these, what we call interfaces. So sand, where you can see the ends and beginnings of these rocks and shells. Or if we actually put ice in that drink, now you can start seeing these interfaces, these borders. So heterogeneous has borders, which we call interfaces in our world. All right. So here, I did do it. So here all the metals are blue, right? So things you know to be metals, iron and nickel, copper, zinc, maybe you know that's a metal, gold, silver, these are metals. So these are on the metal side. The non-metal side, the oxygens, nitrogens, neons, hydrogen, helium, those. So yeah, hydrogen belongs over here as a non-metal. But anyway, those are things that aren't metal. And then we call these yellow things metalloids that sort of border that staircase. So that staircase would be right here, and it'll be drawn on any periodic table I would give you for this class. So you don't have to really memorize where it is. And then things that touch the staircase are sort of in between. Okay. One thing people get confused about with on this thing is, how do I know if it's a compound or a mixture? And so basically, here's the thing. The law of definite proportion says a chemical compound contains the same elements in exactly the same proportions. So for example, water, H2O, is always water, whether you have a drop of it or a huge bottle of it, whether you get it from the top of a mountain or the bottom of the ocean water always has 2 hydrogens for every oxygen. It's the same proportion. That is not true for a mixture. So a mixture would not have the same proportions. If you think about tomato sauce or salsa or these types of things, salads, these would be mixtures because they don't have the same proportions of things no matter where you go. So compounds have definite proportions no matter where you are, and mixtures can vary based on where you are. These are just some things, right? Even back in ancient Greek times, the Greeks realized that these things were always the same, and they have their exact proportions here. Um, Also, just to let you know that chemistry is a universal language. I can't read much anything else right here. This is all in Greek. I can read that, I guess. But you can always read the formulas. Okay, so here are some examples. Tomato sauce, would that be a mixture or a pure substance? Tomato sauce, hopefully you realize, is going to be a mixture because it varies based on where you are. Now, is that going to be, since it's a mixture, is it homogeneous, where you can see everything sort of as one thing, or heterogeneous, where you can see interfaces? This is where you'll ask me, like, well, what are you talking about tomato sauce? Let's say you can see herbs and spices, so therefore we're talking heterogeneous. Potassium carbonate, I will typically give you a formula because I don't imagine you know what potassium carbonate is yet. Once you see a formula, you should know that is a compound and therefore a pure substance. Potassium and carbon, potassium is on this side of things and carbon is over here, oxygen's over here. So since it contains things on either side of that line of metals and nonmetals, that would be an ionic compound. Okay, nitrogen is just something right from the periodic table. It's right there, so that's an element, that therefore a pure substance. That's an element, and it's a nonmetal. Hexane, I'm giving you the formula. It's in an exact proportion, so therefore it's a compound. Oxygen or hydrogen compound. Carbon and hydrogen are both considered nonmetals, so that would be considered a covalent compound. That's covalent. Gold is right off the periodic table. That's an element, and that's a metal. And brass is considered a mixture because it has copper and whatnot. So that would be considered homogeneous because you can't really see where the copper begins and the zinc ends or whatever. All right, so those are some examples of that. Periodic table, some things about the periodic table. It's arranged by properties. So the alkali metals family are sort of that first column. The second column are called alkali earth metals. They have similar properties, so they put them all together. Groups are running up and down, so that we call these groups. You know, the boron family or boron group, and the carbon family, carbon group. These are groups going up and down. Periods run left to right, so periods are running like this, like rows. And they're basically 1, 2, 3, 4, 5, 6. Those are the periods. The groups or families are a little different. You should know halogens. You should know noble gases. You should know transition metals for this stuff we're doing right now. Okay, so here are some elements. Metals tend to have luster. They're mostly solid. They're ductile, which is a word that means you can pull them into wire. Malleable means you can hammer it with a mallet and sort of make them shape. So hammer. They're good conductors of heat and electricity, which is why we use them in wires. Those are properties of some metals. So again, on a test, I might say, which of these is a metal property or something? Non-metals are gases. They're brittle solids. They don't really conduct, and they come in a variety of colors, whereas metals are pretty much silver or goldish. All right, so again, as every periodic table you have will have a staircase on it. The metals will be on this side of the staircase. The non-metals will be on this side of the staircase, and these metalloids that touch the staircase sort of have an in-between. So they're semi-metallic, semiconductors, right? Because metals are conductors, so these are semiconductors, and that's what's important when we make computers and whatnot. So that's just what the metalloids are. Ionic versus covalent, we talked about already. So if you have a metal and a nonmetal, that's an ionic compound. If they're both nonmetals, that's considered covalent. And we'll get into some properties of this, hopefully. Types of changes. I think we're going to stop there for now.